Session. My name is Alexander Karokin. I'm an organizer of this program together with Daniel Feldtram, somewhere there, Emilian Parau from University of East Anglia, Frank Smith, somewhere here, and Vernon Squire from Otago University. So 5 of us working on this program. However, this week our boss is Professor Marchenko from Svalbard University. He is chair of this workshop, so responsible for everything. So if something goes wrong, then you can come to him. If something goes well, write us email. Good program. And first presentation after lunch is by David Cole. It's a structure property relationship for sea ice modeling and experimental validation. 1 hour is for presentation and discussion.
Thank you very much. And would like to express my appreciation for the honor and pleasure of talking to the group here. So Alexei, thank you for the invite. It's a marvelous place to be. It's my first visit here, so in many respects it's a first. One of the firsts is that, so we get our marching orders from Alexei that we need to fold in the mathematical aspects of what we're doing. So that came through a little late. I'm a procrastinator, so it was fine. I could just, as I was putting it together. So what I've done is generated sort of a sea ice sandwich. I don't really know exactly where the mathematical interests are, but we'll see a lot of equations. I have a fairly detailed model that is fairly advanced, but I think mathematical approaches nowadays can make this sort of model, a physics-based model, more accessible in applications. So I'll be groping a little bit there, but at any rate, so I'll pose a couple of questions. We'll get into some sea ice properties and processes, and then I'll wrap up after we kind of wrestle through some gnarly constitutive equations with some comments about where I think things might go. So there'll be a few little pictures scattered throughout. I've done a lot of field work in the Arctic and Antarctica, and so these will be a little smattering of my own shots from places I've been. In the interest of cutting time a little bit, I've kind of pulled out a lot of the sea ice pieces of this in favor of the mathematical modeling. I have a ton of backup slides, and I'm here all week. If people want to follow up in any particular aspect, feel free. My time is yours. So today I'm just going to hit the highlights. I will answer in some new work a question that's been unanswered for decades, having to do with the high temperature behavior of ice, and I'll answer an unasked question about the in-situ elastic behavior of sea ice as well. So let's go to it. Here are my sponsors over decades, at least 3 decades. Always appreciate them. At any rate, I'm going to plow through a little bit of introductory material. We are primarily going to be talking about a physics-based, dislocation-based model. So I'll give you a tiny little primer on that. I'll ask you to grin and bear it if you have no idea what I'm talking about, ask questions. But I think it'd be important to get some physical understanding of this model that I'll be developing, because it generally has very good applicability not only to sea ice, to atmospheric ice, and to ice sheets and glaciers. I've kind of taken a cross-cutting approach. I don't consider myself a glaciologist or strictly a sea ice mechanician, but I work in the mechanical properties of ice as it spans a number of different fields. So at any rate, having done a little bit of teaching and having my spouse be a superb teacher, she said right off, well, what are your learning objectives for this talk? Here they are. I will talk a bit about this, what are called structure-property relationships. I'm going to relate the physical properties of sea ice to the mechanical properties. Dislocation mechanics are in here. You will get a good dose. And then I'll ask you if, probably before the end, if there's time, if anybody can decipher my final learning objective, which hopefully will emerge, maybe not. A little bit of freakonomics for you, first of all. In the late 70s, early 80s, huge spike in oil prices. Every oil company was knocking on our door, wanting people to work with them on sea ice mechanics. That died right with that precipitous drop in oil prices. Not that they didn't continue their Arctic activity, but the research efforts dropped off in a heartbeat. On the heels of that, there was the tail end of the Cold War, huge defense outlays in the States. A lot of interest again in sea ice mechanics because of operations in the Arctic primarily. Cold War ended, they told us all to go home. So we went home and worked in other areas. Now, with this peak in global temperatures, we see another resurgence, only this one, by my lights, has more legs or more stamina than the previous ones because there are so many driving forces, the energy industry, defense, transportation, everything from atmospheric to sea ice, spray icing on ships and equipment. There's just a huge raft of problems, not to mention the sea ice modeling community in terms of ice dynamics and climate models. So my hope is I'll be talking about a very fundamental level problem here, but there are a number of avenues where this fundamental modeling ability of sea ice in particular, I'll talk about a couple other types briefly, will have applicability. So scale-wise, all right, I've got a really detailed model. It'll be applicable at small scale, probably up to engineering scales of problems. I think this approach can inform larger scale problems. I don't see large Arctic basin sea ice dynamics models invoking anything I have to say. But my work here, I work quite closely with John Dempsey, who will, next month will be talking about the fracture side of things. This type of model informs the analysis of fracture, large-scale fracture experiments, because you always need to be able to separate out what's going on in a crack tip process zone from what's going on in the bulk of the ice. And so this model is definitely going to handle in great detail the constitutive response of large ice masses. So, all right, here's the lead off. The model itself is going to have, especially this anelastic component, which is time dependent but recoverable, is a very strong characteristic of sea ice. It plays a role in pretty much any deformation until you get up to extremely high rates, as in loading periods of fractions of a second. Anything beyond that, the anelasticity is a major contributor, needs to be addressed. The other thing is, with this modeling approach, it's a little bit daunting. A modeler of a larger scale process has to commit to keeping track of a lot of details they might not currently keep track of. And so it is a bit of a barrier, but I will say in sea ice mechanics, I work also with glaciologists. There's a freshwater flavor of this model that I'll talk briefly about. What's the trend in that whole line of study in analysis and modeling is to more detailed, microstructurally oriented, mechanistically oriented models such as the one we're talking about here. But there is a bit of an energy barrier to get everybody on board with that. So what I'm finding is you actually have to go shake the tree until a glaciologist falls out who's willing to work with you on this. Back in the old days, we used to call it throwing your work over the fence. You do some basic research, publish it, and move on. And I think especially the younger folks I see here, that's not the world anymore. And this has been alluded to previously today, is that you do have to collaborate with interdisciplinary groups. on the math side. I think there's an awful lot that someone with really sophisticated math skills can bring to the table, but probably not sitting in a room by yourself. You're going to be out working with a group, attacking some fairly complex, gnarly problems. Great fun, great opportunities for learning your whole career long, in fact. But energy barriers, things like Abacus don't have a credible ice constitutive behavior, constitutive model embedded in there. During each one of those peaks previously, you get some noise from the Abacus people saying, oh yeah, we need to put in a sea ice model, we need this model and that, but it hasn't happened. So right now there's a bit of an energy barrier. Anybody wanting to incorporate a more sophisticated model has to develop their own UMAT. Hopefully that'll change at some point. Maybe somebody with really good math skills and understanding of physical processes, et cetera, can tackle that. I see some moves in that direction, but it hasn't happened yet. Okay, so talking a little bit about structure. Structure properties. What we're trying to do is relate physically observable or measurable characteristics of the ice to the mechanical response. And the way you do that is with some experiments, some theoretical modeling, and exercising your model over and over again. I'm not going to spend a lot of time showing you how well my model reproduces lab results, other than to say it's really good. I think I'll focus a little more on the applications, and then at the end, a couple of the applications I'm showing you hopefully will convince you that it responds very well to laboratory experiments. In the future, the very near future, the next couple papers I'm going to be working on will have to do with applying this model to our large-scale sea ice fracture experiments that I'll be showing you a few pictures of. Okay, so let's start at a single crystal behavior just to get you going. Erland showed you a couple slides about the atomic structure of ice. What we have here is actually a single crystal with the shear planes, the basal planes at about 45 degrees to the loading axis here. And so the way we describe it, you have this very strong preference for deformation on those planes. We call them basal planes. And it is so strongly preferred to deform there, you can just view each crystal as deforming like a deck of cards. They really aren't going to do anything in other directions. Basal sliding is the name of the game. That's what the model is predicated on. This is a polarized thin section. You don't see any color because of the orientation, but you do get a sense of all these slip lines which are generated by dislocations on these basal planes. The model will use an orientation parameter factor, omega, which is basically a Schmidt factor, which converts an axial stress to a shear stress on a given basal plane. When we have a polycrystal, all we do, each crystal has its own orientation, which can be determined by observation, and then we just calculate the average shear factor for the whole polycrystal, and that gives us a quantity we use to describe the fabric. So that's one of the real important physical characteristics of sea ice. It's a real key issue in glaciers and ice sheet motion because this fabric is constantly evolving. Sea ice tends to grow with the fabric and doesn't recrystallize in the way that ice does in glaciers and ice sheets. So in general, the structure and the orientation, the fabric that develops upon growth is the one you would use to characterize it for your calculations with this approach. So just to give you a quick idea of how this structure gets there, freshwater ice grows with a planar interface, and it tends to do a very good job of eliminating contaminants and any kind of second phase in the solution. Sea ice, when you add enough salt to the water, it starts up this dendritic growth process. So you actually have these blades. These are the C-axes are normal to these plates, and the plates grow out in these regions in between the plates, trap liquid brine. and that stays in the material as the growth proceeds. So a little drawing here, you have a few of these boundaries. If you're having trouble visualizing this, if you have kids or grandkids, picture your kid with a jar of jelly, and they go grab your favorite book off the shelf. And they go through your favorite book and they smear jelly down each page, and then close the book back up and put it on the shelf. Okay, so this is what we have here, is the jelly gets squeezed in between layers of paper, and this is actually fairly organized looking the way our illustrator did this. In reality, this is what the page would look like on the right. That is one of those plate boundaries that has trapped a lot of liquid brine looking face on, and there's just one of them. So these are all brine filled inclusions. The darker ones are actually drained out, or bubbles. Most of them are just drained out brine tubes. But these are all lying on a very well-defined plane in between pretty much freshwater platelets. So this view is looking at the book when it's closed edge on. So you see your pages of pure ice, and then each page has this really complex system of brine inclusions on it. One of the things that happens when ice grows this way, for reasons I don't understand but I've fully characterized, is that the dislocation density is extremely high as a result of the growth process. So, this is a little hard to see with the lighting here, but this is the bottom of a sea ice core. That's what this skeletal layer looks like. This is what we call that region of all these very delicate little plates that are growing together, and between them we're trapping the brine. And that exists right at the freezing point at the bottom of the sheet. It also, you don't see it here, and I think I pulled the slide. I have it if you want to look at it. The bottom of the food chain in the Arctic or Arctic regions resides in this layer. And you'll have an algae bloom that is very extensive, and the algae basically lives in this layer. And then very tiny organisms that feed on the algae, and slightly larger, on and on, up through your penguins and seals and everything, all really depend on that algae bloom. So as we lose sea ice extent, we're kind of losing the bottom of the food chain in the Arctic regions, which is a real issue. Not going to get into that. So we can put this ice under cross polarizers. This, because of the birefringence, this shows us individual grains. And so these are the guys we can study and get orientations of these crystals that help inform the model. So when you see that omega parameter, that is the result of computations that have to do with how these grains are all oriented relative to each other and relative to your stress direction. So our brine inclusions don't just sit there. It's very dynamic. All these little odd things you see here, odd-shaped things, are actually tubes and little pockets of brine, but very close, -3 degrees, very close to the melting point. And this was actually photographed at -3, just as a matter of pure luck, down in Antarctica when we were running some experiments one year. But huge volume of liquid brine near the melting point. Conversely, -15, there's this from the phase diagram. You have the brine inclusions close up considerably at low temperature. So you have a really different level of perforation of your ice, the ice matrix, that's very temperature dependent. And that, I'm not going to get into too many details on that here. I'm going to focus more on the anelasticity and the creep. But it's a real key thing to be aware of. On a larger scale, obviously we're kind of working our way up in scale here. These are full thickness slabs. They're 10 centimeter tick marks, so it's like 1.2 to 1.5 meters. Just to give you an idea of the complexity of the flaw structure that you're dealing with, a lot of people are interested in things such as electromagnetic properties of sea ice, optical properties, in addition to mechanics. And so all this business, everything you see here, the light stuff, are basically brine inclusions. So it's very complex sets of horizontal layering, vertical drainage patterns, And as the year goes on and it gets colder and then warmer, this system just changes very dramatically and brine drains out. One final thing on this. Erlen showed a nice photo before. What we see when we do experiments in the field, and particularly fracture experiments, is that these channels are regions of weakness. So if you're propagating a crack through material like this, the crack will preferentially go and root itself through these areas. So you wind up with a very unplanar crack front. Here's what an algae bloom looks like. We ran into those on occasion. And so it can be a lot more prolific than this, actually. But we do look at the crystal structure down through the sheet in addition to looking at the flaw structure and the salinity profiles. Give you a little idea of what our field experiments look like. This is a nice little drawing. We cut a sheet of some size, a few meters up to 10 to 20 to 30 meters. My colleague John Dempsey has done up to 80 meters on a side. It's like a compact tension experiment whereby you introduce a starter crack with a loading device and then some measurement gauges along the crack and then ahead of the crack in the region where the crack will go if it runs straight. My part of this, we will actually do some cyclic loading of the crack at stresses that are below the point at which the crack will propagate. So we can essentially query the whole sheet and get a snapshot of its constitutive response under a given set of conditions, which is something we're actually still working on analyses after quite some time here, but that'll be coming along. My part of this, the model we'll be talking about, does the characterization of the whole sheet. So once you realize you can quantify that, then when you analyze a fracture experiment, you can pull out the constitutive response of the whole ice mass and be left with just the response around the crack tip and the damage zone. This just gives you a little idea. Mount Erebus in the background, spectacular place to do work if you ever have an opportunity. This is on Ross Island. We're out on the sea ice, a few kilometers in McMurdo Sound, working away. We would tend to have our dwelling in near shore and then a few huts out around the actual test site for equipment and such. Aerial shot. Another cool thing about doing field work, you frequently get to ride in a helicopter, which is a hoot. So we got to ride over our spot. This just gives you an idea of 3 of these we did. We'd fracture the large one and then cut off a smaller one and fracture that and so on. You can see the cracks running. And yeah, that's just to give you a little flavor of what's going on. The cracks themselves, we talked a little bit about alignment. It turns out that actually, the individual grain alignments and how they get organized have a lot to do with how the cracks run and the fracture mechanics. If the C-axes are all aligned in a certain way such that their planes of weakness make a long scale pattern, then fracture energy goes down. It's a lot easier to break along that direction. You get these very nice straight, smoother crack paths. If, on the other hand, you have either you're running against that pattern or it's not organized at all on a crystallographic scale, you wind up with these very jagged crack paths as you see here. So part of what we do in the field is characterize this crystal structure so we can interpret these experiments. Otherwise, if you don't do that, you're sort of stuck at trying to explain an awful lot of scatter. So we do cyclic loading at a whole bunch of scales. Lab scale, kind of thermos bottle size specimens in tension and compression. Down here, this is actually about a few centimeters of bonded together snow grains in a very small laboratory experiment. Cyclic loading, see the same hysteresis. 10 meters on a side, floating plate, same business. We've done some scale effects, still work in progress on the fracture side, but on the constitutive side, I'm happy to report we really don't see much in the way of scale effects on the constitutive behavior. And that's going from 4 to 30 meter square samples. So that's good news. A little exercise with model just showing how it picks up primary creep. I'll be talking about this anelastic component, which is time dependent and recoverable. Viscous is the permanent strain that never comes back. Okay, so let's get into dislocations. I got 2 slides and then you're going to be experts. They are linear defects. These are observations, X-ray observations from my colleague Ian Baker at Dartmouth. And what they demonstrate in freshwater ice, these lines are actually dislocation cores. Very well established that they exist. They are very important ice behavior. And my model quantifies all this behavior in terms of these guys. They support shear deformation on basal planes. The other thing that's noteworthy and has been important in terms of understanding polycrystalline behavior is that, okay, grain boundaries in ice are not nice and smooth. They have ledges. These ledges, once it's under stress, are very prolific sources of dislocations. So there's no problem in producing dislocations in ice. Sea ice, as you can see, the guys have looked at it and they go, there's just too many, we can't even count. Just be satisfied that it's completely loaded with dislocations even before deformation takes place. A little cartoon here showing the nature of these. So if you have an atomic structure that has a discontinuous and interrupted atomic plane, like kind of like a sheet of paper partway through a stack, that spot there is a dislocation core. It's a jog in the crystal structure. If this is our crystal structure at various points during straining, our dislocation can actually break bonds and reform bonds along this plane such that from the beginning, it's over here on your left, it passes through the crystal, pops out on the other side. The net result is 1 Berger's vector of straining for this piece of ice. So we have that as our mechanism, and that's been quantified. I got to briefly talk about the components of the model, and then you'll have plenty of equations to chew on. One of the unanswered questions that I will answer is what's the difference between the elastic properties in the lab and in situ? And once we started running some higher temperature tests, we realized that there is actually quite a bit of difference. I'm not getting into the details of how the model calculates this. I'll just point that out. Most of our time will be spent on the anelastic component, which is basically got 2 mechanisms, this dislocation mechanism and then the grain boundary sliding mechanism, both of which are quantified. I'll talk a bit about the viscous straining as well. So here's your quick dose. The elastic behavior is dramatically affected by brine drainage in the field. In the lab, you take a core out and you warm it up. What happens? The pores open up, the brine drains onto the floor. It doesn't stay, it doesn't reside in the ice. So any further warming after that happens, you have a fairly static microstructure. Out in the field, what happens is you have floating ice. The brine inclusions open up when it warms up, but they're in a column of water. So the ice stays in contact with brine, which keeps eroding away the pure ice part of the matrix, and to the point of giving you about 25% of the elastic modulus because of that loss of ice mass in the structure. So the next iteration of the model, which I'm going to be working on after this meeting, will capture that. But if you wind up doing any kind of modeling, looking at lab results, trying to extrapolate to the field, you have to be very cognizant of features such as this. So at any rate, very briefly, the model is deterministic. It's going to have no tunable parameters. We can determine anything with some experiments or physical observations. It's not going to be useful for everything in the world, but anything to do with energy loss and obviously this modeling side of things, it really informs the whole model. And it's a very useful way to query the material anyway. So here's the physical basis for the model. You have a dislocation that's sitting at position X. Its response to a cyclic load is drag controlled. In other words, there's a temperature dependent drag that inhibits as a function of its velocity. And there's also a microstructural stress that is acting on it as a function of its position. Physical quantities described here, nothing arbitrary at all. So one solves that. This is probably really easy for everybody locally here. You wind up with, so we're still talking about one dislocation here, transient term that helps you when you're starting from load 0 into a cyclic response. Material scientists, people will look at in phase and 90 degrees out of phase as the two components of interest. And basically, here's stress. So scaled with our trig function, this B over K is basically the loss compliance due to that mechanism. And we'll convert that. Well, actually, we'll do one other thing first. So we start out with a fairly simple solution. The frequency response is called a Debye relaxation curve. It's a single relaxation time that has a very characteristic relaxation curve. Doesn't work for ice. We have a lot of coupled grains. We have to account for a relaxation time distribution. So there's this real clever little function that I'm just going to substitute in for the frequency dependence of this model that occurs in a footnote only in the 1972 edition of Noack and Berry, anelastic relaxation crystals. I've seen it used a couple places, but it's perfect for ice because we can apply this to both of our relaxation mechanisms. The only criterion restriction on these curves is that they integrate to 1. And so this function, as a function of this term alpha, lets us broaden that peak out in response to the relaxation time distribution quite handily, and it always integrates to 1. What's not to love? So you'll see that kind of repeated through here. If you take that out of phase curve and integrate it, you wind up with what's called the storage compliance. And the out of phase part is called the loss compliance. And both of these are in frequency domain here, are frequency dependent. All these geometric terms do is determine how that relaxation is distributed either in frequency or in time after start of loading, okay? I won't get into the dislocation mechanics, but we can relate our term, our position to the dislocation density, and that in turn drives this loss compliance. So these are the quantities that we're interested in getting at. The model relates those to the actual dislocation density. This is what they look like. So these are broadened out in frequency space because of alpha, and 0.54 and 0.6 for our two mechanisms. The dislocation mechanism is, these are loss compliances here, about an order of magnitude stronger than the grain boundary relaxation. But if you're working at problems, either at low temperature or higher frequencies, the grain boundary relaxation could be the most important one you have. You can take a look at this in time domain. So we typically express this time dependence in terms of what's called a normalized creep compliance function. It goes from 0 to 1, and it gets scaled by our friend here, this delta D for dislocations. There's one also for the grain boundaries. Again, that's about an order of magnitude stronger than that guy. They have different activation energies and slightly different peak width parameters. And here's our function. Basically, it's the storage compliance function works perfectly for this 0 to 1 behavior we're looking for. So in time, each of these mechanisms, the strain is realized according to that function and according to that strength. So pretty straightforward. The other thing we're able to do is the dislocation density gets determined experimentally. There was no real basis for getting this relationship theoretically. So we did, Glenn Durrell, my colleague, went down cellar and came back in about a year, had a huge amount of data at a variety of stresses and temperatures on sea ice. All this original work is done on sea ice. And we were able to come up with this second power stress relationship for the dislocation density. So that's our key parameter that's going to drive the behavior, the constitutive behavior that we're looking at. The other interesting thing here is we also found that the dislocation production has its own activation energy. This has real important implications more in glaciology than in sea ice mechanics, because that crowd has been wrestling for years with all these kind of seemingly unexplainable variations in activation energy. But this model, these values are a little different in freshwater ice, I'm finding out. But basically, if you have a really low stress situation, you're not producing dislocations to any great extent, you have a relatively lower activation energy, the temperature dependence. As you go to higher stresses and produce more dislocations, especially for sea ice, your activation energy can get up to around 1 eV, whereas if there's no production, it's less than half of that. So the temperature dependence of this model and the constitutive behavior of sea ice depends very dramatically on how many dislocations are produced. So just a real quick consideration of viscous straining here. I'm not going to get into what's been used a lot other than Erlen referred to an n equals 3. It's power law dependence, Glen's law it's typically called. Very empirical, and it applies under certain conditions. As in when the dislocation density is really low to begin with, you can get n equals 3 behavior to arbitrarily low stresses. For sea ice, that's not the case. You have a high threshold level of dislocations. That basically makes this a linear problem up to some arbitrarily higher stress. It may be 0.1 or 2 or more MPa, in fact, below which you'll have linear viscoelasticity and you'll have linear creep. And then once you exceed a threshold where you're producing a lot of dislocations, you start to see this transition to n equals 3 behavior. The model captures all that, which I think is a pretty cool feature. And that's one of our transportation things down in Antarctica. I have in the tour bus. So freshwater ice, because I had a good set of creep results just to give you an idea what's going on. So this is log plot of strain rate versus log strain for increasing stress levels in all about the same 1 millimeter grain size. So what this is to show you that in general, in sea ice more or less does this. There's primary creep up to this minimum. That's what Glenn law describes. It doesn't tell you anything about before and after. It just gives you a relationship between strain rate and stress, in fact, for that minimum creep rate. My model, if you play the whole thing, will give you the whole curve. I'm not going to get into the fabric development that produces this, but it does handle that quite nicely. But this primary creep up to about 1% strain, you can generally consider that as a constant microstructure problem. So the structure you get when the sea ice forms, use that in your modeling, and you're good to go. So this is an accumulation of strain rate versus stress, shear, or normal, and published actually quite some time ago, but it was kind of a nice compilation. You see this follow-up, this n equals 3 is what's typically used for ice. Sometimes it extends to low stresses, sometimes not. And according to my analysis and a reasonable amount of my data, that's due to threshold level of dislocations, the initial level. Jackie Richter-Mengi had some nice creep data that I stuck in here. That actually shows his fall-off from n equals 3 at low stresses. I see that in my experiments as well. This just was a nice compilation. So how do we model that? Well, it uses the same mechanism. I won't get into the details hugely, but the viscous strain rate is linearly a function of the dislocation density. You'd say, all right, great, that's easy, linear law. The thing is, we already saw that rho here is a second power function of stress. So when stress is high enough to produce a lot of dislocations, this gives you a third power law. When it doesn't produce, it's just drifting around existing ones, it's a linear law. As we'll see in the application in a minute here, that's pretty handy because we aren't living with a third power stress relationship with a bunch of linear terms. They're all linear until you start producing dislocations, okay? So this is the other new thing, the unanswered question. I got 2 slides on this, but I wanted to share it. People in ice mechanics, this is interesting. Erlen mentioned Barnes, Tabor, and Walker. I actually got a hold of 2 of those guys last year asking for their original data from their famous 71 paper, because that was, I was working on this part of the model and wanted to validate it with as much experimental results as I could find. I finally got a hold of Walker in New Zealand, and he said, "Oh, you're 15 months too late. I just changed offices and threw everything away from his 71 thesis. And the library here doesn't loan out manuscripts. So if I can get in this week, I might be able to copy these things. As it was, I had to digitize their figure. I got some results that are reasonably good. But that was 71, and they pointed out that up to about -8 from lower temperatures, ice seems to have a constant activation energy. It starts to get higher, apparent activation energy. It gets higher, more sensitive to temperature, the creep rate does, with proximity to the melting point. So I normalized a bunch of results here. There's actually this blue line, awful lot of results at very small temperature intervals, right up to -0.01 C, these Morgan results. You see, okay, this for your rate process people will recognize this, but typically the log of a rate versus 1 over T, slope of that is your activation energy. So when you see things bending upwards, there's an apparent increase in activation energy. But what I was able to find by analyzing my results up to about -3, and then these results by Heike and Tamura from 81, they actually did some pulse echo measurements and got dislocation densities right up to the same temperature of the Morgan data, -0.01. And what they saw was this kind of piecewise linear increase, just exactly what Morgan saw. And as I say, my data didn't quite go up that far, but I got this same trend in here at lower temperatures. And it gives you about an order of magnitude jump over the last couple tenths of a degree in dislocation density. That's exactly what's needed to explain the increase in creep rate with temperature up to -0.01. It was right on the money. It was startling. So from 2 completely different, actually 3 completely different experimental methodologies, I was able to zero in on this relationship. And I've got a paper that'll be submitted fairly soon describing this whole piece of it. But this is brand new. It's one of the things you can do as a retired guy. You can sit down and mull over these long-term problems. Most of these are the Barnes, Tabor, and Walker data that I digitized. Glenn did, in the early days, did some -0.02. Sam Kolbeck and Evans here, some actual tests on glacier ice right near the melting point. They were actually done in a glacier for temperature control. And when you put in this factor I've applied to the dislocation density as a function of temperature, it really captures a little bit dodgy at -48 here, but -34 right on through, I think it does a bang-up job capturing this temperature effect and the stress level effect. This is due to a high initial level of dislocations that causes this deviation from n = 3 behavior. I'm not doing anything with microfracturing, but the deviation at high stresses is power law breakdown due to microcracking. Not addressing that at all. So at any rate, that's pretty cool. So a couple of quick applications. You can take the model and formulate it for a series of step changes in load or step changes in strain. And in the former, each load step, again, this is just completely arbitrary, but just to show you the response. The way you would model this is you take the full model, elastic, anelastic, and viscous components. For each step, you would say, all right, here's the step, that's an elastic response, and then in time, you'll have this delayed elastic effect and creep from these other mechanisms. So each step, you would keep track of this tapering off in deformation. You apply another step, you still have to keep track of this guy. That's where the hereditary integral comes into play. And then this new step creates a new little jump, and then it has its own relaxing function according to the model. If they drop, boom, same thing. So you can apply that method of calculation either in terms of an increment in strain, and you just divide that and sum up over all your time steps with the compliances here. In this case, elastic are two anelastic mechanisms, and then the viscous compliance for each step. Now you have to integrate back considerable ways until each one of these steps is exhausted to get the full answer, which would be one of the areas I think that math folks, if you can come up with a more efficient way to handle the hereditary integrals, I would love you forever. That'd be great. And conversely, if you're in stress control, you'll have increments in stress, and then you just compute the, multiply that by the loss compliances to come up with the strain increments as a function of time. And so you do that for each of these loading increments. The viscous, I just pulled out stress here to get a different term, so we can factor out stress since they're all linear. Piece of cake, a little bit of programming, but again, a bit of a computational burden here to handle the hereditary integrals. That being said, you can see how each of those behave. Here's how the model would behave with 3 different increments in strain. And so you hold that strain, and the stress would relax according to these type curves in a matter of seconds or minutes. So this next simulation basically is employing that method of calculation. While I was in Svalbard last year, Nick Heijkoop was doing his master's thesis experiments in strain control, and the group was interested in the cyclic response. And so we spent enough time together, and I was teaching this model basically as part of Alexi's course. And so we said, yeah, sure, we can model that. So this was using that strain increment formulation. This is his input. So the system is controlling the strain of the sample, loads up and applies a few cycles, unloads. Model is still in red here, or model data is still in red, my model's in blue. It's a little bit off here, and I think that's probably more a result of filtering on the input than anything, because it does a pretty good job everywhere else, but there's a bit of a jolt to the loading at first that was real, but I think it got filtered out of the strain data, but the stress data still reflected that. At any rate, the only thing we did here, we weren't sure the dislocation density, so we had to play around. He had kind of low salinity ice, but basically I thought it did a real nice job with the only thing we had to do was set the dislocation density, and then everything else required no tuning, it was fixed. So I was happy with that. The other way you can use the model with experiments, and these are a couple tension experiments on Antarctic sea ice cores. You can basically, the blue would be, all right, this is loading at that temperature and that strain rate. You can, you see a real nice agreement. And then, so you can tell things like, oh, at this point, that's when I started inducing damage. So you can start getting very rational about analyzing these results in terms of damage propagation. This test here was spectacular because it actually captured a few load points as the crack was propagating. So this gives what's called a stress separation curve, which is very unusual in lab experiments. But the same token, we can tell there's basically, looking at the model, that the behavior is all explainable with elastic and anelastic behavior up until the point that the crack started propagating. And then we can actually quantify that stress separation. This is one of the key parameters that the fracture mechanicians need for their kind of analyses. So at any rate, we'll wrap up. Not that everybody's an expert in dislocation mechanics, but at least you saw the nature of the equations and the kind of analysis that needs to be done. It's a bit daunting, but if areas where one could improve the efficiency of the implementation, I think the physics are good to get actually in use, that we need to have fairly robust implementation of this. I've worked with Mark Hopkins here on a very similar problem in contact mechanics, where we implemented in his DEM very similar laws for contact behavior. And it is doable. There's a penalty computationally, but it is doable. Anyone that's interested, and I would agree with some earlier comments, get integrated into a group working on the problem. There's so much here that on your own you're not going to go learn everything there is to learn about a detailed micromechanical model or the properties of sea ice, but you need to spin up on those aspects of the problem, I think, to be an effective player. The younger folks here, I'll emphasize again, if you get good at this kind of modeling, there are many, many applications. It's not just sea ice structural, ice structure interaction, atmospheric ice adhesion problems, the list goes on. Smaller scale stuff in particular, but any interpretation of sea ice experiments, I think in the future is going to require this level of detail. So you'd have a capability and some skills that you could market in a number of different areas. So at any rate, the payoff, this is pretty much what I just said. So why don't we leave it there? Give you a final micrograph. These are all little brine inclusions with some very cool lighting effects to show them off. So thanks a lot for your attention.
We have about 10 minutes for questions, comments, additions.
Can I start? Okay. Thank you very much for this very deep presentation of this part of ice mechanics. But as usual, it's much easier to ask a question than to analyze details. So, very big philosophical question.
Sure.
How this investigation and those relationships can support the solving the global problem of determination ice loads on wide structures in the sea. Definitely the picture of dislocations relates to local strengths of ice local, but how this could be connected with the global?
Yeah, good question, and thanks, Dmitry. So here's my view. There's a couple paths where this kind of detailed model can help the larger community, one of which would be supporting a sophisticated fracture analysis, okay? You can't get at large-scale fracture of sea ice, let's say of intact sheets, without understanding the constitutive behavior, because you have to have that to analyze your experiments. So in that regard, it's helpful as a stepping stone. You wouldn't implement a model like this for the kind of problems that you're worried about, simply because you're dealing with such a large scale and these processes probably already happened. But they would help very clearly in the analysis of the fracturing that goes on to generate the rubble fields, how the ice responds to obstacles, et cetera, et cetera. So, that I think is more on the analytical side before you get to the scale of your problem, for one. For two, I think, and I'll learn more because we have some work starting up this year with Artu Poliarvi at, did I say that right? Love that R. Well, we're actually going to be looking at rubble behavior. So that's an area I have not worked in. I will be working in that. So in a year or two, I might have a better answer for you, because again, we'll be trying to understand experiments that have been executed on large blocks, but under well-controlled laboratory settings. So those are the kind of settings where you need to understand all these things in order to get the models properly formulated to understand how a mass of rubble is going to behave. That's the hope. But on the other side of things, there are a lot of problems to do with ice that I pointed out that aren't ice structure interaction. Although another thing though is the structural dynamic side of things. If you have an intact sheet impacting a narrow structure and you're worried about vibrations being set up, I would think that the anelasticity, which is going to actually give you notice the strain peaks after the stress peaks because of that mechanism. So depending on the rates, you can actually have ice, if it doesn't lose contact with your structure, is actually, after each load peak, is going to still be pushing at the structure. Interacting dynamically with the structure is a consequence of the failure processes. So I think there might be an avenue there for this kind of model to help out. Smaller scale, though, than what you're talking about. Yep.
Yep.
I have some small questions, maybe stupid. Yeah, but as I understand, if you have primary creep, so then dislocation density is constant.
No. It can be. Depends on the stress level.
Yeah, low stress level.
At very low stress level, dislocation density can be constant.
But at the same time, they're moving.
Yes.
So therefore, they can move out, but cannot move in. Therefore, their amount should be smaller.
So, yeah, good point. What's generally taken as the case is that when it's constant, when the dislocation density is constant, that really only means that the level of production equals the level of annihilation. So you'll have these ledges pushing in dislocations on one end, they're getting absorbed in a grain boundary on the other end, but on average, you're not producing more than you can absorb. So that gives you that constant dislocation density, gives you linear creep behavior. Good question though, yeah. Rocky?
Oh,
Oh, yeah.
Sure. Thanks very much. Very nice presentation. I'm just curious. You presented data for sea ice for dislocation density. You said you mapped the density function. Was that for standard salinity sea ice? And have you looked at, for example, if you have brackish ice versus fresh? And I know you have looked at freshwater as well. But is it?
Thank you, sir. Great question. I pulled that out. But yeah, that was, I thought, down in the weeds a bit. We have looked at everything from freshwater up to abnormally high salinities. And there's a nonlinear relationship. But actually, in terms of meltwater salinity, you need to get up to a few parts per thousand before you kick in that dendritic growth that is related to the dislocation density. So yeah, we've got this really cool nonlinear relationship, but it's valid down, like if you're in the Baltic or Caspian where you have lower salinities and you're saying, I got 2.5 parts per thousand, I don't have 5 to 8. We've done some experiment. I could always use more data, but we do have a relationship that would say, all right, lower salinity ice, we do see this lower dislocation density, so it'll be less lossy, it'll be more elastic behaving. But yeah, that's all, yeah, good question.
For the activation energy portion as well, was that strictly for freshwater, or did you look at warm sea ice as well to see activation energy? So my data was all on sea ice, or the bulk of my data. And so I was able to say, yeah, I get up to -3 and I saw that drift. You don't get sea ice at -0.01, so I think realistically there's going to be a sea ice cutoff in that relationship. But what I did find, my activation energy for dislocation and production at 0.45 EV, that I have a lot of data to substantiate that value. I didn't get into that level of detail, but that plot with all the Barnes, Tabor, and Walker data and all, I deduce from that analysis that activation energy is somewhat lower. It might be 0.25, so it's 0.2 of an EV lower in freshwater ice, but the hope is that either Ian Baker and I at Dartmouth are hoping to get some funding on this line, or I can con the Australians into running these experiments in shear, which I hope would work out. So we would actually get those hard numbers for freshwater ice to validate that.
Thank you, David, and thank you all contributors.
Thank you very much.